All right, guys. As we begin to dip our toes into this idea of understanding these chemical reactions, coupled chemical reactions, that these pathways of conversion that allow us to extract with the best possible efficiency these high potential electrons that we want for creating the energy of life, there's some big chemical themes I want you to keep in mind, right? And at the highest possible level of this, the sort of chemical themes, you to remember a couple of the two big ideas here, right? The first is that all of this chemical pathway stuff that we're going to be talking about is going to involve a couple of bigger ideas. The first is that we're going to move stuff around, be it electrons or phosphate groups or whatever, using activated carriers. And what activated carriers mean is sort of similar to that idea we just talked about a couple of videos ago with ATP. You can kind of think of ATP as an activated carrier of phosphate groups, right? It's activated because it's hydrolysis free energy. It's fundamentally unstable. It's thermodynamically unstable. It wants to kick that phosphate group off, but it's kinetically stable. Getting to the transition state that lets that happen is unfavorable, which means that molecule is activated and ready to go. It's my cocked spring analogy, right? And we're going to see that not just for phosphate groups, but in several other situations, right? So that's a big theme that runs through central metabolism, right? The other big theme I want you to keep in mind is that in the gigantic space of organic chemistry that many of you guys were exposed to in your organic chemistry classes, turns out the chemistry of life operates in a fairly small subset of all the possible chemical space available to carbon, nitrogen, oxygen, phosphate. The chemical toolbox that metabolism or that living organisms use is actually relatively limited, right? It's used in an almost vast and varied way, but there is a relatively small space, right? So you can learn some of these sort of general reaction themes and you'll recognize them over and over and over again as they get reused to do similar things in completely different pathways, right? Okay, so those are sort of the two big ideas. And we're going to dig into these sort of, one at a time here. Let's start with this activated carrier idea. So I've sort of introduce that general concept to you a little bit. Let me get a little more specific now. So here again is this idea of activated carriers. We're going to have activated electron carriers, which are the same sort of thing, fundamentally thermodynamically unstable to be charged up with an electron, but kinetically stable. Phosphate carriers, well, I already introduced that one to you. We'll come back to it in a second. And then activated 2-carbon carriers, where there's only one that we're going to be dealing with in the pathways we're going to look at. Right? All right, so let's see, again, a little more detail how this is going to work. All right, so our activated electron carriers, we have a variety of different ones depending on where we are. In many cases, this is going to involve metals, but at the beginning stages of the pathways we're going to talk about, it doesn't. It involves a set of small organic molecules, and the two most important ones are these two molecules. The first is so-called nicotinamide adenine dinucleotide. I'm sure you've heard of it, NAD. Here's NAD, right? It's a dinucleotide. It's composed of a purine ring. There's an adenine, which you'll recognize from nucleic acids. There's its ribose. It's connected through a phosphodiester bond to another ribose, and to then this nicotinamide ring, this 6-membered ring with this hexacycline amide sitting on it. And it turns out that NAD, by virtue of this quaternary aromatic amine sitting there in that ring, is a wonderful place to stuff electrons. In fact, NAD happily sucks up 2 electrons and 1 protons right here on that one reactive site to reduce the reduced form of NAD, so-called NADH, right? And this is an incredibly important cofactor in a wide variety of enzymes, often known as dehydrogenase enzymes, as you'll see, that do things like this, right? We saw this a little bit before when we were talking about my idealized electron flow with methane. Again, not a biological reaction, but it's very common to see alcohols turn into carbonyls, right? And one of the principal ways that that happens in biochemistry is to use the electron carrying potential of NAD to suck up those electrons, right, and a proton to convert that alcohol group into a carbonyl group. All right, so NAD is super important, right? The other big organic electron carrier you're going to see, of course, is a flavonoid. You guys may hopefully remember the flavonoids. Again, business end of this molecule is a little bit different, but the back end of the molecule is just like NAD. Here again, there's an adenine, there's that purine ring, the ribose, and the phosphodiester. There's another ribose, but in the flavonoids, that ring is open. We'll talk about open and closed forms of carbohydrates here soon. I'll remind you of this. In the flavonoids, the ring is open, whereas in the nicotinamides, it's closed, right? And at the other end of this molecule, we have this isoalloxazine ring. And this isoalloxazine ring also is a great place to stuff electrons, but it's a little bit different than NAD. Whereas NAD is only going to take up one proton. You can only put one proton on that site that is on the other side of that sort of positively charged nitrogen, aromatic nitrogen. This guy is going to take up two protons along with two electrons. We'll put one on here and one on here. Each of those two nitrogens is going to take up a proton and an electron to generate the reduced form of FAD, known as FADH2, right? Okay, and I cut away one of the ways in which you would use FADH2 is a situation where you want to put in, say, a carbon-carbon double bond by taking an otherwise carbon-carbon bond, pulling this proton, that proton off, sucking two of the electrons out, and stapling in a carbon-carbon double bond. And the enzymes that would run this type of reaction are frequently going to use FAD to generate FADH2. Okay, so that's activated electron carriers. Next guy in our list, well, okay, I forgot. Let me mention something else here. So we talked about NAD, right, or NADH. Here, that molecule is again. It's worth a little aside here. NAD has a cousin, which you've probably heard of, called NADPH. It looks exactly like NAD, built exactly the same way. The only difference is that the ribose on the 2 position, right, on the adenine down here, in NADPH has a phosphate group on it. Okay, so the question is, well, why do that? I mean, it's the same molecule, right? It's doing exactly the same thing in terms of sucking plus electron. Anybody know what NADPH is used for versus NADH? Give you a hint, maybe as you're thinking about it. This has to do with segregating electron flow in 2 parts of metabolism. And I just pointed it out to you as we've been going through this set of videos for this lecture. NADH and NADPH are segregated from each other in running electron withdrawal or chemistry by anabolic and catabolic pathways. Specifically, NADH is almost exclusively utilized in catabolic oxidation events, where dehydrogenase enzymes take oxidized NAD, yank electrons out of molecular structures, and reduce and generate reduced NAD or NADH, right? NADPH is usually used the other way around. NADPH generally is used biosynthetically, where you have some oxidized small molecule metabolite that you need to build something back up. And in some cases, you need to reduce things in order to do that. And those electron equivalents are usually going to come from NADPH flowing into this biosynthetic route with enzymes that are cousins of these dehydrogenase enzymes. But these enzymes, known as reductases, don't work with NAD. They only work with usually NADP. And that phosphate group is how these enzymes are segregated from one another, right? So they don't interact with the opposite substrate. And then there are all these ways to shuttle reducing equivalents back and forth between NADH and NADPH. It's important enough to understand that that can be done, but that's as far as we're going to talk about it right now, right? Okay, so those are our activated electron carriers, especially here at the beginning of metabolism. As we get on deeper into this, you're going to see electrons moving around using metals quite a bit more. Phosphate carriers, remember those? Remember those, right? Talked about those a minute ago. That was these guys, right? ATP, phosphoenol pyruvate, 1,3-bisphosphoglycerate, creatine phosphate. There are a whole set of other ones, right? This is the same basic idea. If NAD and FAD are activated electron carriers, the reduced forms of those molecules fundamentally are thermodynamically unstable. They want to be oxidized, right? But the transition state for losing those electrons is actually fairly high, right? So once you get them reduced, they're thermodynamically unstable, but kinetically stable. And again, I just sort of keep rerunning this tape, right? Same basic idea here with these phosphate carriers, like ATP, phosphoenol pyruvate, 1,3-bisphosphoglycerate. All right, good. So one more activated carrier we need to think about, right? And that is an activated 2-carbon carrier. And for the part of metabolism we're talking about, we've only got one of these, right? And that's this guy, which again, I'm hoping you've seen before. It's acetyl-CoA. So coenzyme A is built, again, from a similar theme, right? The back end of this molecule looks just like NAD and FAD. Again, it's an adenine dinucleotide. It's an adenine diphosphate, right? So there's that adenine ring. Here again is a ribose. In this case, the 3 position of the ribose is phosphorylated. A little bit different, except for pH has a phosphate, but it's on the 2, whatever, right? So we got a phosphorylated adenine nucleotide, a diphosphoester here, which is then linked up to this pantothenate unit, right? Which is then connected to the real business end of this molecule, which is this beta-mercaptoethylamine, right, through this amide bond. And the thing that really matters right there is that thiol group, right? Because that thiol group on acetyl-CoA is a wonderful place to stick 2-carbon acetyl groups, right? So imagine you have acetic acid here, right? C double bond O, OH, and the methyl group. You get rid of the hydroxyl and you make this thioester bond. That's what acetyl-CoA does. And this molecule, that thioester, is an activated carrier of those 2 carbon groups, the same way NAD is an activated carrier of electrons and ATP is an activated carrier of phosphate groups. This acetyl-CoA, that thioester, is thermodynamically very unstable, but it's kinetically quite stable, right? And it's not going to decay very fast unless you have a key to make that transition state that causes this 2-carbon group to come off of that, to break that thioester bond, right? So you can store it there and move it around and use it where you need to. Okay.